Hey students, it's Mr. Sagers back with another video for Earth and Space Science. Today's topic is star classifications. By the end of today's video, you should be able to identify patterns in stars' brightness, color, temperature, and life cycle stage. Let's get to it. Over the last several centuries, astronomers have dedicated much time and resources to learning about stars. Through much trial, error, and observation, they've developed a method for classifying those stars. But before we talk about the finer details of their methods, let's pause for a minute and ask the question, what does it mean to classify something? To classify means to arrange or organize a group of objects according to qualities or characteristics that they might share. For example, books are classified in a bookstore according to their genre, intended audience, and whether or not they are fictional. Cars can be classified on the basis of model, color, or type, such as sedan, pickup, or SUV. Biologists have gone to great lengths to create a classification system for living organisms that ranges from the kingdoms of life and ends with an individual organism species. In each of these examples, classification is based upon a set of qualities or characteristics that can be used to either group objects together for their similarities or separate them according to their differences. So what are the common qualities or characteristics used to classify stars? From observational data, astronomers have determined that stars' brightness, color, temperature, and the stage of the star's life cycle are all closely related. Let's begin by looking at a star's brightness. The brightness, or luminosity of a star, is largely dependent upon the star's mass and follows this simple rule. The more massive the star, the more bright or luminous the star will be. This is so for a couple of reasons. First, more massive stars have a larger surface area and thus are capable of shining more light through their expanded surface. Second, more massive stars undergo nuclear fusion at a faster rate due to their intense gravity. The increased energy from nuclear fusion causes larger stars to shine more intensely. When talking of a star's brightness, however, there's an important distinction to be made. There is a difference between a star's absolute brightness, which is the sum total of light that the star gives off, and the star's apparent brightness, which is simply how bright the star appears when viewed from Earth. More massive stars would, of course, produce more light due to their greater size. Larger stars, then, have a greater absolute brightness than smaller stars, which don't give off as much total light. The important thing to remember, however, is that not all stars are the same distance from Earth. The apparent brightness of stars, or how bright the star seems to us when viewed from Earth, is greatly influenced by how far away the star is from our planet. The star Sirius A, for example, has a relatively low absolute brightness when compared to more massive stars. But because it is only a mere 8.5 light-years from Earth, the apparent brightness of Sirius A makes it the brightest star in the night sky. Another visible property that is useful for classifying stars is their color. Stars come in a variety of colors ranging from red to yellow to blue. The color of a star is a strong indicator of the star's temperature. The coolest stars are red in appearance. Yellow stars are intermediate in temperature, and bluish-white stars are hottest. An easy way to remember the relationship between stars' color and temperature is to think of a flame. Cooler flames glow a reddish-yellow color. The hottest flames, like those in a blowtorch, shine a bluish-white color. Stars are further classified by their surface temperature, which can range from just a few thousand to over 50,000 degrees Celsius. Keep in mind, however, that these are only the surface temperatures of stars and that the internal or core temperature of stars is usually well over 1,000,000 degrees. The surface temperature of the Sun, for example, is just a balmy 5,800 degrees Celsius. Around the year 1910, astronomers Enyar Hertzsprung and Henry Norris Russell devised a way to classify stars' brightness, color, and temperature by creating a diagram that is still used today. The Hertzsprung-Russell diagram, or HR diagram for short, classifies stars by their brightness on the vertical or y-axis and by temperature and color on the horizontal or x-axis. Brightness or luminosity increases from bottom to top. Temperature increases from right to left. Thus, a cool, dim red star would be classified in the lower right corner of the diagram. Meanwhile, a hot, bright blue star would be found in the upper left corner of the diagram. The Sun is an average-sized yellow star and would be found somewhere towards the center of the HR diagram. Betelgeuse is a swollen red supergiant star whose temperature is cool but whose brightness is great due to its size. It would be classified in the upper right-hand corner. The star Regulus is a massively bright and hot blue star and would be found in the upper left corner of the HR diagram. Here are just a few more stars that we can classify using the Hertzsprung-Russell diagram. The interesting thing about the HR diagram is that nearly 90% of all stars fall somewhere along an S-shaped curve that snakes its way from the upper left corner down to the lower right corner. These are stars that are in the main sequence stage of their life cycle. Remember that stars spend the majority of their lives in the main sequence, so it is logical that most observed stars will be plotted along this curve in the HR diagram. Stars that have progressed to the giant and supergiant stages of their life cycle are found in the upper right corner of the HR diagram. These are stars that are very bright due to their swollen size, but whose surface temperature has decreased. Stars in the white dwarf stage of their life cycle are located in the lower left corner of the HR diagram. These are stars whose brightness is fading at the end of their lives, but that are still quite hot after having shrunken in size significantly. In about 5 billion years, the Sun will swell into the red giant stage of its life cycle. When this occurs, it will drop in temperature, but its brightness will increase due to its swollen surface area. When it can no longer produce energy through nuclear fusion, it will shrink to its white dwarf stage. The star will be much dimmer due to its shrunken size, but its temperature will be white hot because of its densely compacted matter. So to recap, stars can be classified according to shared qualities or characteristics. The brightest stars are usually the most massive. A star's color is closely related to its temperature, and the hottest stars are bluish-white, while the coolest stars are yellow and red. The Hertzsprung-Russell diagram provides a useful way to classify stars by these characteristics, and stars can be found at different locations on the Hertzsprung-Russell diagram depending on the current stage of their life cycle. Well, that wraps up our video on star classifications. I hope you enjoyed it and look forward to seeing you next time. Until then, ad astra.